Hello, 7th graders. We are now starting chapter 7. Now, I'm going to be honest with you. This is some of my favorite stuff that we do. I love solving systems of equations. It's useful, and I don't think it's that hard, but it takes a lot of work. A lot of work. So, we're going to start with kind of going over what this entire chapter is about. So, I'll go over what a system of equations is in a minute, but I want you to write down these 3 ways. The first way to solve a system of equations that we're going to be using is by graphing. This is going to be our first section, which is section 7.1. Now, the next section that we're going to be doing is 7.2. And that gives you another way to solve system of equations. And that way is called substitution. The last way that we're going to solve systems of equations is called the elimination method, or just elimination. Now, many books and many teachers call it many different things. So I'm going to tell you some other ways that you may have heard this or may hear this in the future. And this, by the way, is in section 7.3. This is also called linear combination, and this is also called the addition method. So I'm going to give you 3 tools in your toolbox, 3 things that you can pull out anytime you're given a system in the future. By the way, my 8th graders right now still do systems to this day within geometry problems. So it's something that you're going to be using fluently throughout your math career. So the first section is 7.1, solving systems by graphing. Now, let's go over what a system is. First off, I'm just going to actually write down a system. X plus y equals 7. Now, I want you to think of in your mind what values of x and y make that true. What values make that true? Now, if you graph that, you could put intercepts at 7 on the y-axis, 7 on the x-axis, and graph them. But there's an infinite number of solutions. But then I'm going to give you a second equation. Y minus x equals 1. And my question is this. What value for x and what value for y would make both equations true? What do you think it is? Does 5 and 2 work? Could I plug in 5 and 2 for the first equation and 5 and 2 on the second equation? Could I plug in 6 and 1 or 6 and a half and a half? What value of x and y makes all of this true? Hopefully, you could kind of think of in your head that the y value has to be 4 and the x value has to be 3. So my solution that would make this true is 3, 4. Now, I just want you to watch. Don't write any of this down, but I'm going to show you something. I'm going to make a really, really rough, quick graph of both of these lines. Now, on the first equation, my x-intercept and y-intercept are both 7. So I'm going to put 7 here and 7 here. And this is going to be a really bad drawing. And now I'm going to graph the second equation using intercepts. Well, my x-intercept would be -1. And my y-intercept would be +1. And my line would look like that. Now, actually, you might not know this, but if you graphed 3, 4, which was our answer, guess where that point is? It's the point of intersection. The point at which both of these lines meet is the only answer that makes them true. And I'm hopefully you can take what you've learned from previous years and previous chapters in knowing this, that any solution on this line makes this equation true. Any point on this line makes this equation true. So what point makes them both true? The point where they cross. And that is what we're starting with systems of equations. Now, I don't want you to think that you have to write this entire paragraph down, but do abbreviate. Write down what you need to. A system of linear equations. A system of linear equations is when you have two or more linear equations. So two or more linear equations is called a system of linear equations. Now, one way to solve it is by graphing. We're going to look at all the common points to the lines. Any ordered pair in a system that makes all equations true, it's important to understand that. Your answers must make all of the equations true. And what your answer would be called the solution to your system of equations. All right, so example 1. I want you to solve both of these by graphing, and I do want you to write this down. You do not at all need to use graph paper in your notes, but you're more than welcome to. So I'm going to graph this. So let me load up my graph paper. Now my magic graph paper appeared. Now let's look at our equations. Our equations are y equals 2x minus 3 and y equals x minus 1. Because they're already in slope-intercept form, to me, I'm just going to use slope and y-intercept. So you're going to graph each equation. So let's graph the first one. My y-intercept is negative 3. My slope is 2, which would be 2 over 1, which means I go up 2 over 1, up 2 over 1. I actually do a little more here. I actually draw 3 or 4 points sometimes. It is imperative that you use a ruler or a straight edge. You must use a ruler or a straight edge, otherwise you're going to get things that don't work out. So I graphed my first equation. Now the second equation I'm going to graph using my y-intercept of negative 1 and my slope of 1. So I'm going to go up 1 over 1. Now, this is why we go farther. If you drew your line that looked like that, you may say, oh, they don't intersect, or I'm not sure where they intersect. If you continue your pattern going on your graph, your points should actually pass through one another. So negative 1, and then I go up 1 over 1, and I'm going to go up 1 over 1 again. And it is very clear that my two lines intersect at the point 2, 1. So the point of intersection is 2, 1. So my answer, what is my solution to this system? The solution is 2, 1. Now, if you ever want to know, did I do it right? You plug it in. So I take my value. If I plug in 2 for x and 1 for y on my first equation, 1 equals 2 times 2 minus 3. That works. And then on the second one, 1 equals 2 minus 1. That also works. Therefore, this is the correct solution. Example 2 is on page 375 in your book. You do not have to copy this entire thing down, but I do want you to write down example 2 and the answer. Suppose you are testing 2 fertilizers on bamboo plants A and B, which are growing under identical conditions. Plant A is 6 centimeters tall, growing at a rate of 4 centimeters per day. Plant B is 10 centimeters tall and growing at a rate of 2 centimeters per day. Which system of equations models the height of each plant, h of d, as a function of the days? Well, let's look. Plant A, h of d. Plant A grows is 6 centimeters tall and grows at a rate of 4 centimeters per day. Well, rate slope, we know that. So 4 centimeters per day would be 4 days, or 4 centimeters per day. And then it was already 6 tall. So we know it's 4d plus 6. Our second one, our plant grows at a rate of 2 centimeters per day, and it's already 10 centimeters tall. So that would be 2d plus 10. So my correct answer, 4d plus 6 and 2d plus 10, would be D. D is the correct answer. So example 3, I want you to interpret the solutions. Now we're actually going to graph what we just had. So graph these. Now we already know how to graph, and so I would anticipate you would not have a problem with that. So I'm going to give you the graph, and there it is. So here's my graph. So interpret the solution. Now we know the solution is what? What is the solution? 214. What does that mean? Does that mean in 2 days, 14 butterflies are going to come out of a book and fly away? What's going to happen here? Well, we know X means number of days, and Y, or in this case, it's H of D. Actually, it's D and H of D. So your X-axis represents D, and your Y-axis represents H of D. And H of D is height. So the second number is height. So what does it mean? You can't just say after 2 days, the plant's 14 centimeters tall. What you're going to have to say is this. After 2 days, both plants will be the same height of 14 centimeters tall. Ladies and gentlemen, plant B actually starts off taller but grows at a slower rate. Plant A grows at a faster rate. The point of intersection represents when they're going to have the same height of 14 centimeters. I want a precise, good answer when you're interpreting what these mean. Now you may be thinking to yourself, wow, that's easy. All I have to do is graph and tell me the point of intersection. Yeah, no, that's not right. You have special types of solutions as well, because lines don't always intersect. I've only given you examples where lines do intersect. Lines do not always intersect. So what happens? Well, we can have parallel lines. What do you know about parallel lines? This is important, huge thing. Parallel lines have the same slope, but different y-intercepts. Where do parallel lines meet? They don't. So a system of linear equations that has no solution means that the lines are parallel. Parallel means the lines are not going to meet, which means you are not going to have a solution. So, example number 4, solve by graphing. Right off the bat, I want you guys to be smart enough to look at that and go, bam, there's no solution there. Right here, both of these equations are solved for y. If they're solved for y and you notice, hey, wait a minute, they're the same slope. Guess what? If they're the same slope, they're not going to cross. Now, if you graph them, the first equation has a y-intercept of 1. Our slope is down to right 1. Therefore, my line looks roughly like that. Once again, make sure you use a straight edge. My second one has a y-intercept, a different y-intercept of -1, but the same slope. And that's a really bad line, but these lines are parallel. And your answer then would be not parallel, but your answer would be no solución, no solution. But that's not the only thing, because sometimes your lines may intersect and you have one solution. Sometimes your lines may have the same slope, but different y-intercepts. So therefore, they don't meet, they have no solution. But what happens if they have the same slope and the same y-intercept? Well, think about it. If you have the same slope and same y-intercept, what do you notice about your lines? They're the exact same thing. And therefore, we're going to go to infinitely many solutions when the graphs coincide. They're the exact same line. So let's do an example. An example would be example 5, systems with infinitely many solutions. Solve by graphing. 2x plus 4y equals 8, and y equals -1/2 x plus 2. If I graph these, the first one, I'm going to graph using intercepts. So to find the x-intercept, I plug in 0 for y. My x-intercept would be what? 2x equals 8, which means my x-intercept is 4. My y-intercept is what? It'd be 2. If you can't answer these questions, make sure you study or ask questions in class on concepts you already know. So I graph this, and there's your line. Next, I'm going to graph the second one. Y-intercept of 2, slope of -1/2, so down 1 over 2. And once again, you will notice, and that's a really bad drawing there, this is the exact same line. That's a really bad two lines. But they're the exact same thing. Now, let's say you're doing this. You're like, Mr. Humphreys, I want to solve my equation for y. And you wanted to subtract 2x. And you wanted to divide everything by 4. Negative 2/4 is 1/2 plus 2. Well, guess what? If you have the same line, your equation should be the same. If you're like, Mr. Humphreys, do I really need to graph this? I can tell you they're the exact same line. The answer is no, because you can tell by looking at it, they're the same line. They have the same slope, same y-intercept. There is infinitely many solutions. So your answer is infinitely many solutions. And here is your summary. If you have different slopes, it doesn't matter what the y-intercept is. Automatically different slopes, you have intersecting lines, you have one solution. If you have the same slope and different y-intercepts, that's the definition of parallel lines. Therefore, you have no solution. If you have the same slope and the same y-intercept, they're the exact same line. So your answer would be infinitely many solutions. Way to go, 7th graders. Way to go.